Texas.
What?
Old Texas.
Old Texas, I know.
Might care to look at that, Peter.
What is it?
The essence of a man like me lies just in what he thinks and how he thinks, not in what he does or suffers.
The time had come for the rank amateur to try to grasp the way Einstein thought. Yes, said Nigel Calder, the writer, my journey was really necessary.
There's the observatory now.
What, those two little white, whatever they are?
That's right.
There's a third one I can see now.
Yes, they're the domes. They keep a lookout for aircraft so as not to zap us with their laser beam.
You serious?
Quite serious.
They wanted me to speak Einstein's words and make the odd space flight, but mostly just to attend to the theory of relativity. I was promised a tale of how our perceptions of space and time and color are distorted according to where we are and how we're traveling. Amid such relativity, Einstein found reliable laws governing atoms, planets, stars, and all creation. Ah yes, an escort, perhaps to make quite sure I didn't funk the cerebral adventure they had in store for me.
Very nice flying.
Thank you,
Fred.
sir.
Thank you very much indeed.
On my arrival, I knew only that Albert Einstein was a gentle genius whose reasoning anticipated our world of nuclear energy and space flight, the Big Bang, the black hole, things I'd only heard about. My tutors were to be leading experts assembled in this remote corner of Texas for my benefit and for yours, our guides through Einstein's universe.
Dennis Sharma here is a theorist concerned with the overall nature of the universe. Roger Penrose, he pioneered the modern theory of black holes. You've heard of them.
Yes, I have, without understanding what they are.
Well, John Wheeler here said they had to exist and named them black holes, as a matter of fact. He's very much a grand old man of theoretical physics.
I see. There are some more... Oh, yes.
And Wallace Sargent here thinks he's discovered a huge black hole.
Well, he looks as if he's photographed just at the moment of discovery, doesn't he?
Very pleased with himself.
Yeah, with everything.
Erwin Shapiro, you'll hear how he's been getting radar echoes from the planets.
Yes.
And Sidney Drell's a theorist from the high-speed world of subatomic particles.
Gracious.
And Ken Brescher here, he's checked some of Einstein's basic assumptions with very precise astronomical tests.
A formidable range of expertise, but they look friendly enough. I then became aware that there might be more to those motorcycles than met the eye. As we journeyed into the mountains, Calder told me that the theory of relativity burst upon the world more than 70 years ago, when special relativity proclaimed the curious effects of high-speed motion. General relativity, he said, followed later as Einstein's theory of gravity. But we were to take them in the reverse order and approach the bewildering distortions of time by way of a gravitational black hole.
I'm just nosing in towards the black hole now.
For our celebration of Einstein's relativity and the famous formula that powers the universe, the venue was the McDonald Observatory of the University of Texas, and the observatory's main telescope was our window on Einstein's universe. With a light-gathering mirror 107 inches wide, it's not the largest in the world, but a very impressive instrument all the same.
Oh, that's charming.
Isn't it, though?
Yes.
It's quite a telescope.
Already I found a posse of relativists at my shoulder. And affording us the use of the telescope to embellish our little seminar was the director of the observatory, Harlan Smith.
For proper levity. But you see the gigantic counterweight here.
That's merely a counterweight.
Yes, many people ask what that's for, but it's just dead weight.
The air was decidedly thin on the mountaintop. They bring you up here, getting you in some sense closer to the stars, I suppose, and then present you with stairways at every turn.
More steps?
More steps. Just. You're standing very close to one of the portholes, which the light can emerge. We can put an instrument on there to analyze the light. It becomes the main collecting mirror. But it's also interesting to see the control console down there. It's really remarkably small for all the functions.
You mean that's the dashboard for this?
That's all it takes.
Well, this is McDonald, and this is Kit Peak. This one...
They did everything to help a greenhorn understand modern astronomy in its Einsteinian modes.
NASA tracking station in Madrid, the Bond telescope, the
So basic are Einstein's ideas to modern knowledge that confirming them is now a global industry. When I prowled through the observatory, it seemed like a set for some drama in space. In a sense, it was. About science, Einstein and I had only this in common. We both hated the way it was taught to us at school. He transcended that, I drowned in it. John Wheeler began my rather belated rescue.
Thanks to your not being a scientist, we're all going to have to give this account the simplicity that Einstein would have loved.
Where do you think we should start the account, John? With gravity?
Nothing could be better. Everyone has to deal with it every day.
Gravity. Well, let's see what the astronauts made of gravity on the moon.
I'm very proud to have the opportunity here to play postman. What could be a better place to cancel a stamp than right here at Hadley Rill?
I remember this from the time.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
I have here a hammer and a bird's feather. How about that?
If you were Galileo, how would you, in the light of that, try to persuade people that everything falls the same rate?
Difficult.
Difficult. Air resistance is a whole problem, isn't it? So such a wonderful thing that air resistance for objects like this doesn't count so much.
Fantastic.
What a feat for Galileo to realize that everything falls at the same rate. But for Einstein, it was a still greater act of imagination to realize that the reason those things all move the same, they get their moving orders from the same piece of space. It's not the distant Earth, it's the space right where they are.
Yeah, there came to me the happiest thought of my life. Consider someone in free fall, for example, from the roof of a house. There exists for him during his fall no gravitational field.
And Einstein really tells us that gravity is an illusion. I can toss across to Dennis a ball, and that arc looks as real as anything could be. And I can toss the ball across to Sid, and the arc looks as real as anything could be. But Einstein tells us that the arc is a pure illusion. If we could only cut away this grid with a welder's torch from underneath us and all fall freely, then as I toss that ball, it would move in a beautiful straight line. Einstein tells us that in a local, freely falling frame, there is no gravity. Einstein would have loved to see those astronauts in Skylab. They were weightless. They were in free fall. Einstein's great idea, all objects fall because they get their moving orders right from space. Skylab had no power in orbit, and no force acted on it. It went just as straight as possible through space. But space is warped around the Earth. So Skylab could end up, and did end up, going in a circle. Warp space was Einstein's style of thinking. Moving about in warp space is no more mysterious than traveling about in these mountains. You just can't go in a straight line. To go in a straight line, you must go down on the plane.
Well, like everything else, light, it seems, responds to gravity, and so space is warped. Coaxing me over that fence was Erwin Shapiro.
One of the important questions we have to decide is whether something is straight or warped. How can we do that? We need some frame of reference. For example, if you were to look at this line of posts and trying to decide whether they were straight or not, how would you do it?
Well, you'd presumably look along it. I think I could have told from there, but it's almost straight.
Right, you squinted along it, and really, your frame of reference was the light rays. And that's a very good technique. However, you can get fooled if the light itself gets bent. For example, water bends light, and we can illustrate that here, these two rulers. I put these two rulers in the water and ask you to decide whether the bottom one or the top one is actually straight.
Well, since water bends light, the bottom one looks straight and obviously isn't.
That's right. See, when we pull it out, when they're out of the water, you can see clearly that the bottom one is the one that's bent,
yeah.
And the top one is the straight one.
Mm.
In fact, if you look from the Earth at light from a star beyond the sun's gravity bends the light of the star as it grazes its limb. And so the position of the star appears to change. Einstein calculated the bending of light using this idea of curved space.
As seen from the Earth, certain fixed stars appear to be in the neighborhood of the sun and can be observed during a total eclipse of the sun. Now, at such times, these stars ought to appear to be displaced outwards from the sun as compared with their apparent position in the sky when the sun is situated at another part of the heavens. A ray of light going past the sun undergoes a deflection of 1.7 seconds of arc.
That prediction in 1915 led to world fame for Einstein. In fact, there was a total eclipse of the sun in 1919, and a team of British astronomers went to observe this total eclipse in the tropics. And here's a plate taken from that expedition of the sun during the total eclipse. This is a negative, so you don't see the sun at all. It's blank field.
Yeah.
And these black striations are the solar corona. And very tiny black dots are the stars in the field of view. And the relative positions of these stars were measured very accurately and compared with corresponding measurements of a photograph taken of the same stars when the sun wasn't in the field of view. And the results showed the star position shifted during the total eclipse in proximate agreement with Einstein's predictions, and certainly quite different from what Newton would have predicted.
Newton, forgive me. You found the only path barely open in your time for a man of the highest powers of thought and ordering. The concepts which you created still guide our thinking in physics even today, although we now know that they will have to be replaced by others, farther removed from the realm of direct experience, if we aim at a deeper understanding of relationships.
Nowadays, we needn't await a total eclipse of the sun to attempt to make measurements of the deflection of light. We can use radio waves. According to Einstein's theory, radio waves, just like light and X-rays or any other light-like radiation, is predicted to behave the same way under the influence of gravity. Instead of ordinary stars in our galaxy, with radio waves we observe the much more distant objects called quasars. Just like for visible stars, quasars seem to change position in the sky when the sun comes into line with them. With the radio technique, we can also achieve far better accuracy. The most accurate measurements were done at the National Radio Astronomy Observatory in Green Bank, West Virginia. This experiment confirmed Einstein's prediction for the bending to within about 1%.
Powerless then to question that gravity bends light, we tried our skills with an impressionistic model of warped space. They urged me to believe that the distortions of space due to a massive body like the sun could shape the course of lesser objects like the planets. The table maker gratuitously added bottomless pits of gravity, black holes that would swallow an unskillful ball.
Black holes aren't getting much to eat today. Einstein wouldn't be happy if we didn't tell you his story in the simplest words. Space tells matter how to move, and matter tells space how to curve. That's it. Throw this ball past the sun. That's light changing its direction, but not through some mysterious force acting through space, but through the warping of space itself. Or put a planet into orbit around the sun and watch it go. And where does it get its moving orders from? Not from that sun, but from the space right where it is. Or put Skylab into orbit around the Earth and ask those people on Skylab, what do they see? They get their moving orders from space itself, right there where it is. Einstein's wonderfully simple picture of it all. or the moon going around the Earth. Pull the Earth away, unwarp space, and the moon will fly off, happy to go in a beautiful straight line.
But cosmic space isn't, after all, a distorted tabletop. I bared my misgivings to Dennis Sharma.
How on earth, or rather, how in the universe, can nothingness have shape?
That is indeed a difficult question, and the Greeks struggled with it very much. They had a geometry of their own, and light responding to that geometry would move in straight lines. That's not at all the case in Einstein's theory. He uses a different geometry from the Greeks, a geometry in which space is warped, and light responding to that geometry doesn't move in straight lines but is bent. And a planet responding to that geometry would move, let's say, in a circle around the sun. Einstein himself was very concerned to stress this difference from the old geometry, and he tried to make it plain to all of us.
On the basis of the general theory of relativity, space, as opposed to what fills space, has no separate existence. There is no such thing as empty space, that is, space without a gravitational field. The geometrical properties of space are not independent, but they are determined by matter.
It seemed that either Newton's force of gravity or Einstein's warp geometry would keep the planets circling in the same stately fashion. But who was right?
In Einstein's theory, the orbits are predicted to be slightly different than they are in Newton's theory. For example, let us consider a single planet in orbit about the Sun. In Newton's theory, this planet would be predicted to follow an elliptical path, that is, a path sort of like a stretched out circle. And in Newton's theory, this path would be followed continually, ad nauseum, following the same elliptical path all the time. Whereas in Einstein's theory, this path actually swivels around. That is, the ellipse rotates very slowly in space.
Near the Sun, gravity is a little stronger in Einstein's theory than in Newton's, so close in the planet teeters for a moment before climbing away.
This different prediction of Einstein's theory actually cleared up a 19th century mystery about the orbit of the planet Mercury, the closest one to the Sun.
The ellipse corresponding to the orbit of Mercury is not stationary with respect to the fixed stars, but rotates exceedingly slowly. The value obtained for this rotary movement is 43 seconds of arc per century. This effect can be explained by classical mechanics only on the assumption of hypotheses which have little probability. On the basis of the general theory of relativity, it is found that the ellipse of every planet must necessarily rotate in this manner.
In the late 1960s, we used the Haystack radio telescope in Massachusetts to measure the swivel of Mercury's orbit. This telescope is enclosed in a radome to protect it from the wind and the sun. What we did was use this radio telescope with an attached radar system to send pulses of radio energy towards Mercury and to detect the echoes. In fact, although the power in the transmitted radar signals is about 500,000 watts, enough to supply the electrical needs of a small town, the echo we detect is so weak that its power is even less than that expended by an average housefly crawling up a wall at the rate of only 1 millimeter per millennium. By measuring these echoes from Mercury periodically over several years, we were able to detect the swivel of Mercury's orbit because the echo delay is different for a swiveling than for a non-swiveling orbit. Our results confirmed Einstein's prediction to within 1%. There's an amazing object that's been discovered in the sky that swivels in its orbit far more than Mercury does. This object illustrates beautifully Einstein's relativistic effect. The object is called a binary pulsar.
An object lying far off among the stars, the binary pulsar, was evidently quite invisible. By what new ingenuity could they track its orbit? Kenneth Brescher patiently explained.
Imagine a rapidly moving vehicle coming down the road, a motorbike, say. As it comes towards you, you hear a high-pitched roar. When it passes you, the pitch drops. There's a change in frequency according to whether the source of sound is coming towards you or going away. That's the Doppler effect. The same thing happens with light or with radio waves. Police speed traps use Doppler radar. It sends out radio waves that bounce off the vehicle and come back with a higher frequency. The faster you're going, the more the frequency is changed. The Doppler effect is an unbeatable way of measuring relative speed. Now imagine an object circling, giving out its own radio pulses. You'd find the frequency rising and falling repeatedly. You could tell it was circling even if you couldn't see it. Completely out of sight among the stars, there's an orbiting pulsar. It's nature's gift to the relativist. A pulsar is a collapsed star, a neutron star we call it, which ticks like a very accurate clock, emitting regular beeps of radio energy. This particular pulsar changes its beep rate in an 8-hour cycle as it sweeps forwards and backwards.
But did you discover this binary pulsar?
No, I didn't discover the pulsar, but all of us who are working on relativity and astrophysics are incredibly excited about it. It's a unique object and a unique opportunity to test the laws of general relativity in a very precise way. It's being studied at the Arecibo Radio Observatory in Puerto Rico. Joe Taylor and Russell Hulse of the University of Massachusetts discovered it, and Taylor has been checking up on it every few months ever since.
Right on source? Yeah. Following errors? No, you're right. Good. Okay. So, is everything still going all right?
One of the marvelous things about it is the changes are so predictable that when they switch on, the pulsar always clocks in right on cue. The pulsar is in a very tight, fast orbit around another collapsed star that's not directly detectable. And the pulsar's orbit changes in the Einsteinian manner. It swivels 30,000 times faster than Mercury's orbit does, 4 degrees a year.
The binary pulsar is very nice evidence for Einstein's effect. But really to milk it for all it's worth in confirming relativity, Taylor still has years of work to do.
And in fact, there's something still more exciting in prospect, which is that as the binary pulsar goes round, according to Einstein, it radiates gravitational waves. The result of that would be that the orbital period would change slowly, and Joe Taylor is trying to detect this change. In fact, just the other day, Joe Taylor sent me a new manuscript of his in which he claims to begin to measure this effect, and it does seem to fit Einstein's theory very well.
These gravitational waves that Einstein predicted are ripples of warped space. And with the help of a computer, theorists have made movies of gravitational waves that ought to pour out from violent events, like the collapse of a star. And there's an interesting kinship, isn't there, between gravitational waves and the familiar tides of the sea that are raised on the Earth by the warped space around the moon.
We're a long way from the sea here, so we can't actually see the
ocean moving up and down the way it does in a spectacular fashion on the coast. But as a matter of fact, at this observatory, they have measured how the rocks of the Earth move under the moon's influence. They move up and down by as much as a foot twice a day.
Unsettling to think of the Earth heaving like that. But the force of the tides gave a certain palpability to warped space. Wheeler then offered me a warped miniature table and a jar of quicksilver.
You'll notice that you have one of the blobs of mercury pulled right out, stretched out, and nothing is a more beautiful illustration of a tide effect than that. But you can, if you like to illustrate that gravitational waves are also tides, take that blob of mercury and jiggle it, and you notice it changes its shape, first this way and then that way. And there just isn't a more beautiful illustration of what a gravitational wave is than the tidal stretching of that little glob of mercury, or the tidal stretching of a gravitational wave detector. One of the things that interests me most about the whole thing is the push it's going to give to technology, because looking for gravitational waves, we have to get down to what everybody calls the quantum limit of measurement. And that's a new thing in the world. And it's going to be new kinds of equipment that show up all over the map. Engineering, biology, medicine, what have you.
You can try to detect very slight ringing in great supercooled metal cylinders like the one at Stanford in California. In Glasgow they have a different method.
Look at some of the details of the optical system down in here.
Ronald Drever uses laser beams that shuttle to and fro many times. And that's to measure shifts in the position of different masses, shifts that might be caused by gravitational waves washing through the Earth. But it's incredibly delicate. They're getting ready to look for movements far, far smaller than the width of an atom, between masses mounted about 30 feet apart.
It's possible that stars going around one another very rapidly can be detected. It's possible that violently exploding stars like supernovae will be detected. And it's even possible that objects falling into massive black holes will produce gravitational waves we can pick up. And if any of those things happen, we'll be seeing the effects Einstein predicted of warped space propagating actually with the speed of light.
The McDonald Observatory had its own laser, and after hearing about clever experiments in other places, I was to see one in progress myself.
Used to that.
We've put those waves of gravity behind us, Peter, and come back to basic issues about gravity and orbits in warped space. What they do here is shoot their laser at the moon to check its distance and movements to within a matter of inches. The moon's a heavy object, but the Earth is heavier still, and they might respond differently in the sun's gravity. Then we might see the moon's orbit drifting a few feet closer to the sun, and Einstein would be wrong.
Fantastic sight of the moon.
The moon looked splendid. No amount of scrutiny by science can efface its terrible beauty.
You probably want it back now, don't you, Robert?
Yes.
Yes. Very wise.
To reflect the laser pulses from the moon, the Apollo astronauts set down a series of corner cubes on the surface at various locations, exactly like the cube corner I have here in my hand. Take a look at it. You look in at this face, and you'll see that no matter what direction the light enters the corner cube, it has the remarkable property of coming out again in exactly the same path, but in the opposite direction. The Soviet Union landed 2 Lunokhod vehicles on the surface of the moon, and each of them carried an array of corner reflectors that were built by the French. And tonight, we're going to try and get echoes back from one of these Lunokhod vehicles, Lunokhod 21, which you can see in the upper right-hand corner of the moon over there.
Oh, yes.
Eric Silverberg took up the story.
We fire the laser every 3 seconds, which produces an extremely intense pulse of light that starts at the far end of the room and then expands up through this tube, hitting 2 reflections and then more until it fills the entire mirror, 107-inch mirror, which gives us a very parallel beam of light to send up to the moon. We typically fire from 300 to 400 shots in each 45-minute period. Since the laser pulse is about 3 feet long, going up to the moon, we can very accurately time how long it takes to get there and back. We always have to station an aircraft observer outside the dome to keep track of any possible nearby aircraft because of the intensity of the beam. We're going to start ranging on the reflector now, and Robert will start firing at the Soviet site. His job is the most demanding because he has to point the telescope with an accuracy which is equivalent to trying to hit a penny at a distance of perhaps a mile. And we help him out as much as we can by putting a small red flash on the image of the moon in order to show him precisely where the beam is pointed. In really good conditions, we can get a return back on this teletype perhaps every 5th or every 10th laser shot. And when that happens, they ring a bell so that Robert knows precisely whether or not he's located at the right position.
But even with such precise measurements, it's not easy to calculate the moon's orbit because of the myriad of small effects that influence its motion. My colleagues and I used the measurements made here at McDonald to actually compute the moon's orbit to very high accuracy and found it to agree very well with Einstein's claim. So Einstein's theory has again withstood another stringent test, and rival theories are put under much greater constraints if they're going to be in accord with the behavior of nature.
Fantastic.
I left them contentedly ringing the bell for Einstein while tending a half-baked bun of comprehension in my brain. I pictured the moon faithfully circling in the warp space around the Earth, and the sun's gravity toying with our own great planet.
Einstein wouldn't be happy if we didn't tell you his story in the simplest words. Space tells matter how to move, and matter tells space how to curve.
Warped space didn't trouble me too deeply. I remembered how easily any exercise in straight-line geometry can be botched. If the young Ustinov could bend the world, why not Einstein? But to step onto the quicksands of Einsteinian time, that was uncanny. Unsuspectingly, I watched next morning as a visitor, John Engelbrecht, measured the speed of light.
I'm generating the light pulse with a sparker, which I'm going to turn on here. And that creates sparks, essentially short beams of light, that travel across to the other dome where we have a mirror, and the mirror reflects the beam of light into this telescope right here, where we have a photomultiplier tube to pick up the light signal so that we can look at it on the oscilloscope right here. We measure the time interval by measuring the distance between the two blips on the oscilloscope, where distance across the screen is time.
Looks like about 450 nanoseconds.
And the round-trip distance is 134 meters.
Yes. Well, it's not bad. You've determined the speed of light this morning to be about 298 million meters per second. an accuracy of about 1%. The speed of light is, in fact, Peter, known to great accuracy. It's one of the most precisely known numbers in all of physics. The National Bureau of Standards in the United States has a figure of about 299,792,457.4 meters per second.
0.4?
Well, the National Physical Laboratory in London perhaps would disagree with the last figure.
Ah, yes, I thought so.
Einstein was emphatic that the velocity of light is always a constant, no matter what the motion of the source or the motion of the observer. I've checked this, in fact, using not light, but X-rays, which are a form of light, but at very high energies. In 1970, a satellite was launched off the coast of Kenya for the purpose of doing X-ray astronomy. It was called Uhuru. It discovered and began observing a peculiar class of star. An X-ray binary pulsar gives off regular bursts of X-rays while orbiting at a high speed around another star. Now suppose that Einstein were wrong, and that X-rays go faster if they're launched when the pulsar is moving towards the Earth. Then X-rays from that part of the orbit could overtake X-rays that are coming from the other part of the orbit, making a simple picture quite complicated. For example, you could see the pulsar coming and going at the same time. Peter, from my friend Ethan Schreier at the Smithsonian Astrophysical Observatory, who worked on the Uhuru satellite, I got the following tracing of X-ray pulses coming from the X-ray pulsar Centaurus X3. And as you can see by looking at these pulses, they're absolutely regular. Each pulse comes along at a specific time interval, and there are no spurious ghost pulses lying in between the pulses that we see here. This is direct proof that the speed of light is indeed independent of the velocity of the source. I looked at 3 separate sources, the most distant one lying in the small Magellanic Cloud. The light took 200,000 years to arrive at the Earth from that source. And in all that time, the pulses emitted when the pulsar came towards us never overran those that were emitted when it went away, by more than a factor of perhaps a part in a billion. Well, to put it in earthly terms, that would be about the speed of a turtle moving along the ground.
That's a very earthly term.
In deference to this evident obsession of Einstein's, I accepted that in cosmic space the speed of X-rays, or visible light, or radio waves, never varies. But, dear me, how promptly that golden rule was broken.
If we send radio pulses to another planet like Mercury or Venus, when they're on the other side of the sun from Earth, they can appear to be slowed down by the direct effect of the sun's gravity on the waves as they pass near the sun.
It looks from where we are as if the sun's gravity acts very like a lens, bending the light and slowing it down.
About 15 years ago, it occurred to me that this increase in the travel time was a direct consequence of Einstein's general theory of relativity. In those days of increasing science budgets and low rate of inflation, it took less than 2 years to convert that idea into a very sophisticated radar system which we installed on the Haystack telescope to make these measurements on Mercury and Venus. Now, the actual predicted effect is very small. It's only 200 millionths of a second out of a total round trip time of about 1,500 seconds, or approximately 1 part in 10 million. And we were able to measure it with an accuracy of approximately 5 or 10% with this radar experiment. Now, if we could turn to Mars.
You can't expect a very good image of Mars just now because it's right on the far side of the sun and it's close to the horizon, but maybe we'll get an impression.
Mars is now very near the far side of the sun as we view it from Earth, and is in a good position to see this effect. And in fact, the last time Mars was in this position, we used radio waves sent to the Viking spacecraft, which were landed on the surface of Mars, to measure this predicted slowdown much more accurately. And with such measurements, we were able to verify the predictions of general relativity on regard to the slowdown to an accuracy of about 1/10%.
Okay, you say light slows down near the sun. But Ken Brescher told us just now that light seems always to go at the same speed. I think, Peter, that as a theorist, Roger Penrose here might resolve that contradiction for us.
Yes, well, you see, it really depends where the measurement is done. If you measure the speed of light as it appears at the surface of the sun from here, then it would seem as though it slows down. It would seem as though the sun was surrounded by some sort of lens that should not only slow the light but also bend the light. Whereas if you did the measurement at the surface of the sun, then you would get the same answer for the speed of light as you get for the speed of light at the surface of the Earth.
We had come to the nub. To keep his blessed speed of light always reading the same, Einstein decided that time itself must slow down near a massive object.
So gravity has the apparent effect of reducing the speed of light and slowing down time. So that if you imagine the extreme situation of a black hole, then light would be reduced to zero speed, apparently, and time would apparently have been stopped completely at the surface.
Apparently. Well, I feel awfully guilty at asking this because I'm opening, as they say here, a new can of peas, but we've heard so much about black holes. What is a black hole, apparently?
Yes, well, according to Einstein's theory, if you have the final fate of a very massive star would be an object so concentrated that light itself couldn't escape from it. The object collapses inwards and signals, light, any other kind of signal, any object cannot escape from this region into which the star would collapse. The black hole that results from the collapse of a star several times the mass of the sun would be an object several miles in diameter. But if you, say, imagine the Earth compressed right down until it became a black hole, the dimension would be a bit less than an inch, something like that.
That's the Earth?
The Earth would have to be compressed into that size to be a black hole.
I see. So we shouldn't be candidates.
Don't worry.
I see.
Light at the surface of a black hole trying to escape would hover there forever. And judged by us, looking from a safe distance, time there appears to stop. You'd wait forever for the next tick of the clock. A short distance away from the black hole, time does seem to pass, but rather slowly by our reckoning. We can think of the black hole to be surrounded by shells, in which time runs progressively faster. That's what happens in the immediate vicinity of a black hole, but the effects on time extend for thousands of miles, with time getting gradually closer to what we regard as the normal rate. If you imagine that little black hole with the same mass as the Earth and surround it by a sphere representing the Earth's surface where we live, our clocks run at the appropriate rate. There isn't really a black hole at the center of the Earth, but time at the Earth's surface is slowed a little, just as if there were, compared with the very gradually increasing rates of time way out in space, high above the Earth's surface.
The observer will interpret what he sees as showing that one clock really goes more slowly than another clock. So he will be obliged to define time in such a way that the rate of a clock depends on where the clock may be.
Peter, the interesting thing about general relativity is that my clock, whether I'm sitting here on the surface of the Earth
when I'm orbiting around a black hole will appear to me always to be running at the same rate. The gravitational effects don't change the actual clockwork mechanism and don't affect it in any way. Nonetheless, from your point of view, you might see my clock running at a different rate, and we would appear to have time running at different rates. We could correct for this, and general relativity in fact tells us exactly how to do that. But the clocks themselves are in fact not disturbed by the gravitational field.
Yeah, I don't quite understand one thing, because obviously we are our own terms of reference, and therefore our clocks are our own terms of reference. They become part of us. If I take an aeroplane, as we all do, and fly very high, is what is shown on the clock face affected by the fact that I have flown high, or not by the time I arrive?
Yes, it is in fact affected, and when you come back it will read differently from the identical clock which you left behind, which didn't take part in the airplane ride. But although the clock reading is different when you come back on the ground, the clock, once it's back on the ground, will continue to run at the same rate it used to run on the ground, so that the difference in reading will then remain constant as time goes on.
The important point is that this effect is not a psychological effect. It's a genuine, measurable physical effect.
In the last decade or so, extraordinarily accurate atomic clocks have been made which are sensitive enough to see these very small effects, such that, for example, the difference between the rate of a clock running on the ground and one running on the second story of a building could be observed and measured very accurately.
Oh, so Big Ben's been wrong all the time because it's about the 8th floor.
Right, it's gaining relative to your clock.
I see.
My common sense was outraged, of course. Yet, recent results have evidently smothered all expert and inexpert doubts about Einsteinian time. Sidney Drell set the scene.
The atomic clock is not just an instrument for scientific laboratories to run their equipment with, or as part of their play equipment. In fact, in everyday life, it sets the time by which we live. Here one has a crystal oscillator which keeps time relative to an atomic clock whose signal is being received here with due allowance for the time it takes for light to bring the signal here. Here is the time that it's reading out. I notice that my own crystal watch is 2 seconds slow by the time given there.
Mine's 6 seconds out. That's terrible. This will go back to the maker.
Back in Washington, there sits the master atomic clock against which all other time is referenced for an international time standard. The atomic clocks keep time to an accuracy which approaches 1 second out of 1,000,000 years. That is how far they have come. To understand the atomic clock, we have to now enter into the theory of atoms. And this is another theory, the theory of how light is emitted, absorbed by atoms, and how light propagates with very sharply defined frequencies. There's another theory to which Einstein made very enormous contributions. Sometimes we think of the year 1905, when Einstein was 26 years old, as one of the miracle years of the world, because in that year, when he was giving us special relativity, Peter, he was also giving us the theory of light occurring in discrete packages and with precise frequencies. It was in fact for this work that in 1921 he received the Nobel Prize, when the relativity theory was still viewed as too mathematical, too controversial, and not really of practical importance.
Also at Washington, they keep the clocks that directly answer your question, Peter, about how time passes in an aircraft. Carroll Alley of the University of Maryland and his colleagues put one set of atomic clocks aboard a US Navy airplane, and this was starting in 1975. And you remember on the moon those man-made corner reflectors? Well, the aircraft carried one of them to throw back yet more laser pulses, providing a link to another set of clocks kept in a cabin on the ground for comparison.
The same types of atomic clock?
Yes, they're twin brothers in effect. The prediction of general relativity is that as you get higher above the ground, the grip of gravity on time weakens and your clock should run a little faster. The laser flashes coming from base serve to check the time recorded in the air against the readings of the clocks on the ground while the aircraft flew around and around Chesapeake Bay. The ground radar kept track of it. The aircraft's speed, by the way, also had a very small effect on time by a quite different prediction of relativity, but the experimenters took that accurately into account.
Yes, I'm sure they did.
The main effect on time related to the aircraft's height. At 35,000 feet, the airborne clocks gained about 3/billionths of a second every hour, and each flight lasted about 15 hours, and 5 flights like that accurately confirmed the effect of gravity on time. So Einstein's account of how the world works triumphs yet again.
To punish me for my contempt for authority, fate made me authority myself.
And what's true of atoms in an atomic clock is also true of atoms in ordinary objects like an apple. And perhaps we could draw some of these threads together by telling how, in a time shell, starting at the top of the tree and moving into a time shell lower down, an apple manages to accelerate in the way that's so familiar. It's moving into shells, very fine shells, of ever-slowing time. Its atoms are operating more slowly. It seems to be losing internal energy, which has to reappear in some new form, and the form it takes is energy of motion, so the apple is going faster and faster as it moves down into slower and slower zones of time, until finally it hits the ground and that energy of motion is destroyed.
Well, Nigel, just two little points I'd like to clarify before we all go further into this adventure. It seems to me that the apple has acquired such a particular status with Newton that perhaps one ought to realize for uninitiated agriculturalists that pears and grapes and, in fact, people are subject to the same laws, that pears are not exempt.
Exempt from the action of gravity? Well, certainly not, because especially since Einstein, the emphasis in present thinking is that gravity affects everything in just the same way. And in the case of people, our atoms also are affected in their rate of operation according to whether we're living down in the valley or up on the mountain.
I found the propositions of general relativity easy to state. Gravity bends light and warps space. Gravity slows down light and slows down time. Bewilderingly simple, really, as their full meaning sank in.
You could think, if you dared, of visiting a black hole and hovering there for a while. And there, in the slow-running time shells close to the black hole, perhaps only a few years would pass while hundreds of years were passing on Earth. Maybe you'd like to imagine yourself as twin brothers testing this theory.
The adventurous one is my twin brother Peter, and my cautious one is Albert. And Peter wanted very badly to investigate this black hole. He's always been reckless.
You coming?
You silly boy.
Ah! It's going to be great up there. Not kidding. How about that?
That's the last we've seen of Peter on this earth, anyway.
Would I dare make the imaginary journey to the black hole now proposed? Well, why not?
Goodbye. Goodbye. Oh, do take care. I shook the dust of the 20th century from my feet as my imagination bounded towards the black hole. I'm just nosing in towards the black hole now.
I'm just nosing in towards the black hole now.
Well, at least that black hole has slowed down the hectic pace of his life, but I only hope to God he takes care. The rate of time seemed entirely normal to me, but on the Earth, it was evidently racing along.
The gravitational effects don't change the actual clockwork mechanism. Nonetheless, from your point of view, you might see my clock running at a different rate.
Pictures from the Earth showed the days passing in a matter of minutes. I saw who won the Grand National in 1990, but I shan't tell. It was hard to make out what Albert was saying in Mission Control.
Prudence! Wine has been very good. And that you have looked after your life support system very well, and that you're not drifting too near the edge of that pernicious black hole that causes us all so much trouble.
Anyway, you're with us in spirit, and we'll be able to celebrate any moment now. Yes! A happy new century! Peter, yes. Mr. Bloody Bottle! I see, you look very spry. What? Yes, you do. 21st century?
Very good.
We're still 20 years off then, I reckon.
As years passed on Earth and only months on my spaceship, my greatest concern was for Albert. My twin brother was aging before my eyes. As for me, I was only a few months older.
Well, it would appear that Mr. Einstein was right, eh, Peter? As you can see, I'm still trying to look after you in spite of nurse.
It wasn't long before the Earth forgot all about me.
Time to go home.
Before I could even think of playing Rip Van Winkle in the world of the 21st century, there was one visit I had to make. Alas, poor Albert. Even in imagination, this time travel by means of gravity seemed a joyless enterprise. There was no method for retracing my steps through Einsteinian time and returning to the 20th century.
We've talked about the warping of space, and about the effects of gravity on time, space and time. But relativists like to combine the two into space-time, with time as being the fourth dimension.
The non-mathematician is seized by a mysterious shuddering when he hears of four-dimensional things, by a feeling not unlike that awakened by thoughts of the occult. And yet, there is no more commonplace statement than that the world in which we live is a four-dimensional space-time continuum.
Here we are at a certain place in western Texas, and time 11:30. Put the two together, I clap my hands, that's an event in space-time. Now each of our lives is a series of such events strung together into a world line in space-time. And here we meet together, our world lines more or less intersect. In order to get a picture of space-time, it's convenient to think of space as represented as a two-dimensional flat plate, and that frees the third dimension to represent time. Now, let us imagine an object which is stationary in our description. Then this would be represented by a vertical straight line. An object which is moving uniformly but with some velocity would be represented again by a straight line, but now tilted over. What about an object which is accelerating? Then that would be represented by a curved line. This is the world line of the object. Now let's think of the sun. That again, thinking of it as stationary, would be represented by a straight line. Then the Earth, in orbit around the sun, would be represented by a spiral line. But then the Earth, as we know, is in free fall and should therefore be represented by as straight a line as you can draw. And how is it that it's drawn as this spiral line? Well, this is because the space-time is really curved. Now remember our deformed billiard table. The space then would be warped in a certain way, and as the space evolves to give us our space-time picture, the whole space-time is slightly deformed, and this is why the apparently curved picture of the spiral motion of the Earth is really as straight a line as you can have in this curved geometry.
And I gather that I feel the burden of gravity here on Earth because I go against the grain of space-time.
Gravity feels the same as acceleration, but according to Einstein, in an important sense, gravity is the same as acceleration.
In a gravitational field, things behave as they do in a space free of gravitation if one introduces a reference system which is accelerated. You want me to try it?
Try it.
Get off the ground with me in it.
What Einstein called a reference system which is accelerated was for me a curiously dumpy helicopter to be flown as jerkily as possible. I've ridden some awkward steeds for the movies, but nothing quite as undignified as Dr. Scales. As the helicopter lurched upward, my weight increased, each brief acceleration adding pseudo-gravity. Whenever we climbed steadily or hovered, my weight went back to normal. And when the pilot let the machine accelerate downwards, a nasty feeling, but oh, how the pounds melted away. In some neglected slot machine of my mind, a penny dropped. When a vehicle accelerates, lurching in one direction, all its loose contents are left behind and seem to fall in the opposite direction. As the master said, it's just like gravity. Acceleration could also put me on different scales of time. Stand by, Albert.
it's not only gravity that affects the rate of a clock and so the passage of time. Even motion can do that. And Einstein showed that already in 1905, 10 years before he developed the general theory of relativity. What Einstein showed was that if an observer moves out into interstellar space at high speed and finding himself amongst the stars, then turns round and comes back at close to the speed of light, while the journey for him will seem short, for the people who stay at home it will seem much longer. For instance, he will find that he has aged less during that journey than the person who has stayed at home.
There's a lot of reading, and I suppose you get nothing.
A little lonely up here in space. Long after I'd fired my motors to turn for home, my twin brother Albert was still receiving signals sent by me on the outward leg of the journey. It's lonely up here in space. Again, time seemed to me to pass normally. But it was in this melancholy phase of my return journey that I observed poor Albert growing older by the hour.
That's right, too, sir.
Just as for the visit to the black hole, this high-speed relativistic flight plan took me on a one-way ticket into the 21st century. Although he lived before the space age, Einstein made many imaginary journeys like this. Gedanken experiments, thought experiments, the physicists call them.
One could imagine that the organism, after an arbitrarily lengthy flight, could be returned to its original spot in a scarcely altered condition, while corresponding organisms which had remained in their original positions had long since given way to new generations.
Einstein said that many years ago, but people for many years didn't really accept that notion. It, in fact, was the source of much argument and was elevated at times into the notion of a paradox. But now, with very fast-moving atomic particles, we have displayed this effect with extreme accuracy. Most precisely, atomic particles in a storage ring at CERN, so-called mu mesons, which normally live a very fleeting fraction of a second, perhaps a millionth or 2 millionths of a second, have been shown to have their lives extended by a factor of 30 or so, just by having them move at speeds very close to the speed of light.
Well, I understand that this is possible for particles, but it does sound rather like science fiction to me, and like fantasy. Would it be really possible for this to happen? For people, I mean.
Well, this is a matter of faith, not a matter of science. There's nothing in principle, I believe, that stands in the way of getting one up to speeds that are a significant fraction of the velocity of light. When one thinks of the incredible things that we do with instruments these days, measuring with accelerators that are many miles long, times to precisions of billionths of a second, I would be the last to think it's impossible and won't be done. After all, we did send men to the moon and look for how many centuries that seemed impossible.
Presumably one of the great advantages, though, would be if human beings ever attempted to travel between the stars, that you not only gain in an apparent extension of life as compared with the Earth, but also you can travel greater distances than you would think possible by normal reckoning of speeds from the Earth.
I would say it's not only an advantage, it's a requirement, because the distances to other stars and their presumed planets are so great that there's no way we're going to ever explore them if we don't stretch out our time scale.
It was one of Einstein's earliest ideas in relativity that you could distort time and space just by traveling fast enough. We now left gravity and general relativity aside for a while to hear instead about special relativity and the strange effects of motion.
Now let's imagine that these bikes are capable of, say, half the speed of light. That's what their speedometers show anyway, fractions of c, the speed of light. What kinds of Einsteinian effects can we illustrate with bikes like these?
Perhaps we should start with the simplest point of all. From the point of view of the rider, he's at rest, and it's the landscape that's rushing towards him. In Einstein's democratic universe, that point of view is just as valid as yours or mine. And then recall the Doppler effect, the change in frequency and color of light. An object rushing towards you looks blue because the light gets crowded together. It has a higher frequency. When it's going away, it looks red because the light gets stretched out, and then it has a lower frequency.
I'd like to emphasize something there, Peter. Compared with ordinary white light, blue light has a higher frequency and more energy too. But red light represents a low frequency and less energy.
Einstein made two important discoveries about the Doppler effect. First, it doesn't make any difference who's said to be moving. It's just the relative speed that counts. Einstein's second discovery about the Doppler effect is that when a high-speed vehicle is just passing you, strange things happen. Imagine that you were quick enough to photograph it with your camera. You ready, Peter? As the vehicle passes us by, you'd think it would be neither redshifted nor blue-shifted because it's moving perpendicular to our line of sight. But in fact, it's slightly redshifted. What's more, it's rotated away from us.
Not shortened? Many accounts of relativity would have the bike squeezed short.
No, it still appears to be undistorted, but slightly rotated away from us. But from the point of view of the rider, there could be very peculiar distortions of the scenery if you rode past buildings, say, almost at the speed of light. Perhaps the first thing you notice is the building and the truck curve in a little. Then, as you speed up, you see that they seem to be twisted towards you. Indeed, as your speed increases closer and closer to the speed of light, you start seeing the far sides of the building and truck. You seem to be seeing right around the corners. It's like walking through a rainstorm when your front gets wet and your back stays dry. The light approaches you from unexpected directions.
Consider two bicycles coming at each other at close to the speed of light. You might think that their combined speed, the rate at which they are coming together, is faster than light. But from each rider's point of view, it's not like that at all. Their combined speed, as they measure it, always remains less than the speed of light.
Einstein launched his disconcerting ideas from very simple premises. The riders demonstrated why time runs slowly in a fast-moving vehicle. They just rode in company and threw a ball to represent a signal, a flash of light. From their point of view, the light went straight across between them. But from our point of view, as onlookers watching the bikes go by, the signal went obliquely and on a longer path.
But light always moves at the same speed, so that the time it takes for the signal to go from there to here takes longer from our point of view than from the point of view of the riders. So Einstein tells us that their clocks in the moving frame move slower than ours in exactly proportion of this line to this line.
High-speed travel also makes you seem heavier. Time for a rapidly moving bike slows down and it accelerates more sluggishly. Mass means resistance to acceleration, and the bike's mass piles on as it gets near the speed of light. In fact, it continues to grow more massive without limit as it gets very close to the speed of light, so that in fact it never can go faster than light. But from the point of view of the rider, his mass seems the same as usual. When Einstein realized just how much the way things look depend on where you stand, he also saw a danger. Because, he reasoned, the laws of physics must be the same for the rider as for the fixed observer. Special relativity was born brilliantly out of that requirement, but the price Einstein exacted from us was the scrapping of the old ideas about time. Einstein realized that although each person's view of events is a little different, everyone's view is equally valid, and yet we are observing, all of us, the same laws of physics.
And the touchstone for the reliability of physical laws was Einstein's old obsession, the speed of light remaining constant amid all the commotion of the cosmos.
Now, because of its motion in orbit around the Sun, our Earth is traveling at a speed of about 30 kilometers a second. If the principle of relativity were not valid, we should expect the laws of nature to depend on the Earth's direction of motion at any moment. But the most careful observations have never revealed any lack of equivalence of different directions. This is a very powerful argument in favor of the principle of relativity.
But Einstein's revelation shook the planet. From the reasoning of special relativity emerged a law of creation and destruction. It was time for us to consider the realm of the atom, where relativistic events are more usual than on the roads of Texas.
Of course, for real motorcycles, the velocities are much too low for the effects of relativity to be noticeable. Even for the spacecraft circling the Earth every 90 minutes, the speeds are too low. They move, in fact, about 1/40,000th the speed of light, and their increase in mass due to motion is less than 1 part in 1,000 million. Astronomers looking at distant stars and distant objects are seeing systems moving with a substantial fraction of the velocity of light. And when we enter the atomic realm, we enter into an area where the relativistic effects are very noticeable. Even on your television screen, the electrons that paint the television screen are moving with perhaps 20 to 30% of the velocity of light, and thereby their mass is increased to the order of 1% or so. Out at Stanford, at the Linear Accelerator Center, we produce the highest energy electrons in the world. They come so close to the speed of light that their mass is increased by a factor of 40,000 compared to what they started with. As a result of this very high velocity and high energy that they acquire, their clocks are slowed down. And they don't realize that they have moved the full 2 miles of our accelerator. In fact, from the electrons' point of view, their clocks are moving so slowly, they think they have gone only 2.5 feet by the time they come to the end of the accelerator. At the end of the accelerator, we also have a storage ring, so-called spear ring, where we smash the particles into one another. We create new matter. And in this way, we can very accurately measure the conversion of energy of motion into matter and into mass, and in this way confirm with great accuracy the Einstein equation E equal mc squared.
What an equation that is. It looks so innocent. E, energy, M, mass, and C, not the speed of light, but the square of the speed of light, an enormous number, so that a little mass is worth a lot of energy.
It's hard to appreciate what an enormous leap of intuition and imagination it took to come to this simple formula. Einstein had been thinking from the age of 16 to 26 consistently about the nature of light and electromagnetic radiation. And almost as a byproduct of his thinking on this subject, he came to the following conclusion, that if you look at light, say from the sun, and if you were moving towards the sun, as we've already discussed, the light would become bluer. Now, the blue light has more energy than the white light we normally see, and therefore, he reasoned, there must be more energy apparently coming from the sun. But if that energy is not drawn from any change in the motion of the sun, it must mean that that energy is coming from the mass itself. And so he concluded that the mass of the sun itself is converted directly into energy. He then made the enormous leap to generalize this result to all forms of energy. In the 19th century, there had been energy of motion, and energy of light, energy of heat, but not interconvertible. And so he came to the startling conclusion that all mass and all energy are in fact equivalent.
We are led to the more general conclusion that the mass of an object is a measure of its energy content. It is not impossible that with materials whose energy content is variable to a high degree, for example, with radium salts, the theory may be successfully put to the test.
What Einstein is noting here is that the energy release in nuclear reactions is so great that there is actually a measurable change in the mass that can be detected, and his formula can be verified. The nuclear burning, together with the Einstein relation E equal mc squared, solve a long-standing riddle, namely, how is it that the stars, the sun, can burn for billions of years without running out of material? This equation, E equal mc squared, and the efficiency of nuclear burning were tested quantitatively in 1932 by Cockcroft and Walton with their accelerator, who verified it for the first time.
But it was a long time before any practical use was made of it. Einstein was hounded out of Germany. He came to Princeton, where I had the pleasure of seeing him after his arrival. But it was 5 years from that till that fateful day when I went down to the pier in New York, and the ship came in with Niels Bohr and the word of the discovery of the fission of uranium. January 16th, 1939, and not long after that, Einstein wrote that fateful letter to Roosevelt with all its consequences.
Extremely powerful bombs of a new type may thus be constructed. I understand that Germany has actually stopped the sale of uranium from the Czechoslovakian mines.
And it was hardly 200 miles from here across the desert that first dramatic explosion took place that brought us into the true atomic era.
Einstein, who set it all in train, was appalled by the nuclear arms race. It's ironic that this humble, gentle man who had been an avowed pacifist should now be etched in the history of mankind as the father of nuclear weapons. He believed, as do many today, including many scientists who are familiar with the devastating effects of these weapons, that survival in a world with nuclear weapons is one of the great challenges of our generation. It was, I believe, his last official act to endorse a manifesto in 1955 with Bertrand Russell, which I believe you have here.
Yes. We appeal to you as human beings, to human beings. Remember your humanity and forget the rest. If you can do so, the way lies open to a new paradise. If you cannot, there lies before you the risk of universal death.
I think in talking about Einstein's great achievement, we should really stress the fact that it lies at the basis of all life. The nuclear weapons are only a small byproduct of human folly. Even when I strike this match, a minute amount of the mass is converted into energy. If I took all the mass in this match and converted it into free energy, there's enough energy here to lift the entire mountain on which we're sitting now about 10 feet off the ground. This energy plays a role in the hum of a violin, in the growing plants here, and in fact in the expansion of the universe.
All of astrophysics is about nature's attempt to release the energy hidden in ordinary matter, the energy defined by the equation E equals mc squared.
So I learned to perceive the sun, hot enough in Texas, as a natural nuclear furnace and a typical star. Energy can create matter, so matter has hidden energy. Falling down, like the apple, can liberate some of it. So Wallace Sargent led me back to gravity, saying it can overwhelm a star.
When the sun grows old, it will first of all become a red giant in which it becomes much bigger and a little cooler than it is now. At this time, the Earth will be consumed, but fortunately it will not happen for several more billion years. After that, the sun will shrink and become a white dwarf, which is about the size of the Earth. During this time, a lot of hidden energy will be released, but not as much as has been released by nuclear burning at earlier stages of its evolution. Stars much more massive than the sun end their lives as supernovae. That is, they undergo gigantic explosions. During this event, the inner parts of the star is driven inwards in an enormous implosion. This forms a neutron star, which in turn becomes a pulsar. The matter in the neutron star is extraordinarily dense, and the atoms are crushed together, and a substantial fraction of the hidden energy originally in the star is set free.
Well, so neutron stars exist, but theoretical calculations tell us that something of, say, 3 times the mass of the sun can't exist as a neutron star. It's really only a short step from a neutron star to matter being crushed by implosion into a black hole. In the case of a collapsed star 10 times the sun's mass, say, the resulting black hole would be only about 40 miles across. Nothing could escape from it, not even light. Material falling into such a black hole would liberate tremendous energy just before disappearing into the hole, giving out intense X-rays. And these X-rays could be seen from the Earth, and that's in fact how we could expect to detect such a thing. Well, the X-ray source called Cygnus X1 meets these specifications and may well be a black hole, and it's sucking material apparently from a companion supergiant star.
Now we're on Cygnus X1. What we can actually see here is the companion to the star, not the black hole itself. The black hole is orbiting around the star that you can see.
This is a record of the X-ray emissions from Cygnus X1, and you see there's no regularity in it, as there would be if it were a neutron star.
No, they're not very regular, are they?
The quest for black holes was for me the culminating proof that Einstein's theories still inspire the very latest research. It led us to distant galaxies of stars, as big as our own Milky Way, but erupting most violently.
In order to explain many of the phenomena out there in the universe, we have to invoke enormous energy sources. And it looks more and more as though black holes may be the only possibility to provide such large sources of energy. In this kind of theory, an enormous black hole with a mass probably several billion times the mass of the Sun sits at the center of the galaxy and releases energy in some way which we don't yet understand by swallowing entire stars and gas from the surrounding galaxy. For the past couple of years, several of us have been paying particular attention to the galaxy M87. It's a very distinctive galaxy with a jet of luminous matter poking out at one side. M87 is a strong source of radio waves and also X-rays, and altogether it's a very energetic galaxy. Most of the work that we've done has been observations at the Kitt Peak Observatory in Arizona and at Palomar Observatory in California. We've used a very sensitive light detector brought out from London by Alec Boxenberg. What we do is to look at slices of M87 at different distances from the center and use the Doppler shift to tell how fast the stars in the galaxy are moving around. What we find is that the stars in the very center of M87 are moving around much more rapidly than we would expect. As far as we can see, they're moving fast because they're orbiting around an invisible object, and we can use the speeds of the stars to estimate the mass of this invisible object. It turns out to be about 5,000 million times as big as the Sun, just about the kind of mass that we would expect for a black hole if it really is powering all the phenomena that we see in M87. The problem is that the volume you would expect for a black hole at the of the mass that we think the one in M87 has is very small indeed. And so really the problem is to try and resolve much smaller angular distances.
Small angular distances. I suppose that's the penny at a distance of a mile again.
In order to try and do this, I've turned radio astronomer and with colleagues used the radio telescopes at Goldstone in California and at Madrid in Spain, 5,000 miles away. The object is to try and get a telescope as large as the Earth, by means of which you can resolve very small distances.
Well, I'd just like to know at this juncture, to what extent is all this a logical consequence of Einstein's work, or has it already taken off on its own?
Well, it was certainly not known to Einstein that black holes would be a consequence of his work. On the other hand, later work, since Einstein died, in fact, has pointed very clearly to the fact that within his theory, at least, within general relativity, this is a very clear prediction of the theory.
And of course, independent of the actual nature of the underlying object, we know that it has to put out a great deal of energy, because we see that directly, and that implies a huge underlying mass from E equals mc squared. And of course, the light that we get directly from the object as analyzed by Weil-Sargent obeys the Doppler effect and comes to us as photons. So the richness of Einstein's ideas bears on the entire range of actual observations of these objects.
A computer charted the fathomless warp of space in an imagined collision between two black holes. Our ancestors frightened themselves with dragons and hobgoblins. We have jaws and black holes. In fact, at the dead center of a black hole, I found that even Einstein's ideas falter.
Theory of general relativity can now be adequately applied to the black hole itself and a certain distance in. But it's possible to show that even the theory itself predicts its own downfall. And this is one of the things which was not appreciated before Einstein died. But certainly, everything does get compressed into a very, very small region. And there comes a point somewhere where new physics has to come in. The argument really is at what point and what new physics comes in.
Of course, when you're at states of very high density, you can no longer deal with gravitation in isolation of all the other forces of matter, the strong nuclear forces, the weak forces of radioactive decay, and the electromagnetic forces. Nor can you stay strictly within the realm of classical physics and ignore the quantum ideas.
Absolutely right.
It's ironic that Einstein, who was a founder of the quantum theory through his discovery of the quantum, or the photon, which is the particle of light, never felt comfortable, never felt satisfied with that theory because of the element of uncertainty and the element of chance that it brings into a description of the behavior of particles.
Apprehending more than I could possibly comprehend, I listened like a child allowed to stay up late to ideas that might surpass Einstein's.
On a theoretical frontier, I might say that it seems to me we're no closer to knowing where we're going. They're the very beginnings of efforts to make a supergravity theory, a quantum theory that embraces gravity and the other forces of matter all unified together in this great dream, the grand synthesis that Einstein spent 30 years, in his last 30 years of his life, trying to create and failed. That in alone is a measure, a statement of how difficult the problem is.
When you get down to the size of an elementary particle, the question is, does the concept of space and time still apply at a smaller scale than this? And I think most physicists would take the view that it does apply, and that it goes on until you're down to a tiny fraction of the size of a particle. But the sort of line that we're following is one which suggests that perhaps things go wrong before that. And the idea is that the concept of a point in space is not the primary concept. This is only a mathematical artifact, and that something a little closer to the idea of a particle, although not actually a particle, it's a thing that we call a twister, which is well, it's something I couldn't explain in detail, but the idea is that the concept of a particle and of space itself are both things which emerge out of this more primitive concept. And this is the line we've been pursuing for many years now. And one of the great problems is to see how to tie it in with general relativity in a very clear way. And there are some encouraging features, but it's certainly not finished yet.
From the minutest quantities of space to the immensities of the universe. The director recognized the little boy in me, and he let me drive the big telescope across the sky.
Beautiful, isn't it?
Yes, that's fantastic.
Yes.
The rings of Saturn mapped for me the warped space surrounding the giant planet. As I scanned the Milky Way, Harlan Smith reminded me that the stars, billions of them, and including the Sun, all circle under their mutual gravity. And we looked beyond our own galaxy to similar whirlpools of stars far away in space-time. To sample a few of the billions of galaxies prepared me for contemplating the whole of Einstein's universe and its presumed origin in the Big Bang. And it was brought home to me how Einstein's discoveries about space and time, light and matter, all connect and make a girdle for the universe.
Could we pull Einstein's ideas all together? Energy has mass, and mass has energy. And the mass of the sun, so gigantic, has only to be burned up a little at a time to provide us with all the heat and light and power that we see here on Earth. But that mass has more gravitational pull that pulls light, bends it, pulls other stars. And when stars start flying apart in the earliest days of the universe, that gravitational pull slows down their outward flight. The universe comes into being out of nothingness. Matter, light, energy, all at once. And this matter, this light, and this energy all expand, get more dilute, contract into stars, galaxies, planets, and the whole thing goes on expanding, getting bigger, farther apart. And that's the phase we live in now, as these galaxies are flying apart from each other. But then comes the moment, we believe, down the line, when they stop flying apart. Their gravitational attraction pulls them back together again. The whole thing contracts. Energies go up once more. We get to a gigantic big crunch.
In its pristine form 60 years ago, general relativity clearly required the Big Bang for the birth of the universe. But that melodramatic story conflicted with the astronomy of the day, and Einstein doctored his equations to describe a more restful universe.
In order to arrive at this consistent view, we admittedly had to introduce an extension of the field equations of gravitation, which is not justified by our actual knowledge of gravitation. The introduction of that cosmological term was the biggest blunder I ever made. Death alone can save one from making blunders.
In fairness to Einstein, just about the time that he made this remark, astronomers' idea of the universe were changing rapidly. It was discovered about that time that not only was there our Milky Way galaxy, but there were billions of other galaxies in the universe as well. And more surprisingly, it was found that they were rushing away from one another at enormous speeds. This was discovered by means of the redshift that occurs in the spectrum of the light due to the Doppler shift when things are moving away from us. I'm using this particular machine to measure the redshift of a galaxy. This is the galaxy, and this is the spectrum of the galaxy under a nearby object, which has no redshift at all. When I change the magnification, here is a spectral line due to sodium. And in the distant galaxy, the spectrum line is shifted towards the red. And from the separation of the two lines, one can tell that roughly the redshift is about 7,000 kilometers per second.
Oh my goodness.
This is one of the most important kinds of measurements that astronomers make. We often make redshift measurements. It was first discovered about 50 years ago, and this led to the idea of the expanding universe. Later, in 1965, a radio telescope in New Jersey revealed that the whole universe, even the apparently empty parts of the sky, were aglow with radio emission. This is apparently left over from the birth of the universe. It's this particular discovery that makes the Big Bang theory the dominant theory of cosmology at the present time.
They represented the expanding Einsteinian universe by a balloon studded with galaxies. They told me that its surface denoted the entire universe, with its space curving right back on itself because of the gravity of all its contents. And they induced a cooperative Texan bug to travel in it. In sympathy with that cosmic bug, my mind voyaged among the galaxies. I couldn't really visualize the overall warping of cosmic space. Who can? But I sensed that gravity might indeed close up the universe so that if I traveled far enough, I should find myself coming full circle
back to my starting point.
The buck has nowhere to go but around. There's no end. Nowhere an end to the universe. It's closed universe, but unbounded universe. Einstein's picture was the universe is closed. At least that's what he wrote in the last edition of his book, published in the year of his death, 1955. Today, of course, we don't really know how the evidence is, whether there's enough matter to curve the universe up into closure. But to predict, as Einstein did, the expansion of the universe, and to predict it correctly, and to predict it against all expectation, so fantastic a thing, to my idea, is the greatest prediction that mankind has ever made, and to my mind gives us more faith than anything that we could have, that someday we'll find how the universe itself came into being.
I think it's quite right to have celebrated Einstein out here on the far frontier of Texas, because not only is it the site of a major observatory, and observatories are going to be where Einstein's theories will have to be tested in the distant future, but also because we have all around us still the great frontier of the American West. And this symbolizes, in a way, Einstein's general relativity, which is at the far frontier of the human mind.
The most beautiful thing that we can experience is the mysterious. It's the only source of true art and science. And he to whom this emotion is a stranger, he who can no longer pause in wonder or stand wrapped in awe, well, he's already half dead. His eyes are shut.
It was Einstein's passion to understand the universe. For him, that understanding was the only real power. And he did more to create it than any other man who's ever lived.
Well, that's a very large claim, and I'm sure you're right, but would you agree with that, Wal?
Yes, astronomers use Einstein's ideas all the time, often without remembering who thought of them. It's the ultimate distinction in science, to be part of the furniture, like Newton.
You ask me if one can eventually express everything in scientific terms. Yes, it's possible, but it is useless. It is as though one were to reproduce Beethoven's Ninth Symphony in the shape of an air pressure curve.
I propose a toast to Albert Einstein, one of our greatest heroes. The musicians have Mozart, Beethoven, we have Newton and Einstein. And it's appropriate that most of our talk has been about his physics. But we shouldn't forget the other side, Albert Einstein, the folk hero. Though widely honored, he was a simple man who spurned and shunned wealth, power, status. A refugee on the run from Hitler, he was a dignified and gentle symbol of scientific inspiration that was a great particular inspiration for young refugees and immigrants interested in science. The reputed grandfather of the atom bomb, he was the moral leader of the efforts to bring that dangerous and deadly application of E = mc squared under international control. I propose a toast to the memory of Albert Einstein.
To Albert Einstein.
The most daring proposition in relativity is that the laws of nature must remain the same at all places and at all times, even in galaxies so far away that their light has traveled for thousands of millions of years to reach us. If so, Albert Einstein's own laws of nature, conceived with pen and paper on the planet Earth, hold good everywhere.
What really interests me is whether God had any choice in the creation of the world.